Tonight, we're going to explore one of the strangest blind spots in all of space exploration. Humanity has sent spacecraft to every planet. We have landed on worlds millions of kilometers away. We have crossed the boundary into interstellar space, further than anything we've ever built. And yet there is one direction, the most obvious one of all, that we have barely explored at all. Not across the solar system, but above it. And once you notice it, you can't unsee it. The solar system is a thin disk, a flat plane of orbits that has held its shape for 4.5 billion years. And almost every spacecraft humanity has ever launched moves sideways within it, like a coin sliding across a table. We have mapped outward. We have mapped inward. But the direction straight up, the vertical axis perpendicular to the planetary plane, remains the single most unreached direction in space. No one has ever gone there. And the reason why is stranger than you'd think, which creates a surprising consequence, one that hides something we've never actually seen. The sun's polar regions have never been properly photographed from above. The true shape of the heliosphere, the giant bubble our sun blows around the entire solar system, has never been seen from outside its flat profile. And the one image that seems like it should already exist, the image that would show us what our own solar system actually looks like from above, has never been taken. Not once. Every picture you think you've seen of it is a painting, a guess, an illustration. By the end of tonight, you're going to understand why the solar system formed as a thin disk rather than a sphere, how Jupiter's gravity quietly shapes the invariable plane that everything orbits around, and what it would take to finally lift a spacecraft out of the ecliptic and look back down on the architecture of our cosmic neighborhood. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The solar system began as something nothing about our daily lives would suggest. Not a tidy arrangement of separate orbits. Not a loose cloud of objects scattered in every direction. A disk. A single, paper-thin disk of planets, moons, asteroids, and comets all sharing the same plane, all circling the same star, all locked into the same flat geometry for the past 4.5 billion years. Think about that for a moment. 4.5 billion years. The same orientation, the same plane, essentially unchanged. And yet most of us have never stopped to ask why. We absorb the diagrams in textbooks and museums, the neat rings of orbits drawn from above, or the edge-on cutaway showing the sun at center and planets fanned outward like a thin slice of something much larger. The flatness is right there, presented plainly, and we walk past it. We assume it is incidental, decorative. We treat it the way we treat the shape of a river, as if it could hardly have been otherwise. But here's where it gets strange. The vertical axis of the solar system, the direction we might casually call up or down from the planetary plane, is a direction in which almost nothing in the history of our experience has ever moved. Every spacecraft ever launched, every probe, every satellite, every crewed mission, all of them have traveled within that flat sheet, or have only gently skimmed its edges. The direction perpendicular to the plane, the direction that would lift you cleanly out of the disk and let you look back down on it, remains almost entirely unexplored. Not partially explored, barely touched. The flatness is not incidental. It is the most important geometric fact about where we live. From Earth, you can actually see the disk without a telescope. Go outside on a clear night. The sun tracks a consistent line across the sky through the day. The moon follows roughly the same path. The visible planets, Mars, Venus, Jupiter, Saturn, all of them trace that same corridor. Astronomers call that corridor the ecliptic. It is the disk seen from the inside. We live within the disk, and the disk writes itself across our sky every night. And still, we do not think of our solar system as fundamentally flat. The question is why? Why flat? Why not a sphere of orbits spread equally in all directions? The answer reaches back 4.5 billion years to a cloud of gas and dust slowly drifting through interstellar space. This cloud was not static. It was rotating. Slowly, almost imperceptibly, but rotating. And then gravity began pulling it inward toward its own center of mass. Here is what makes that collapse different from a simple inward collapse. The rotation of the cloud carries something called angular momentum. Angular momentum is a measure of how much spinning motion exists in a system. It cannot simply vanish. It cannot be destroyed. As the cloud collapses inward and the material draws closer to the center, that spinning motion must be conserved. And conservation means speed. The smaller the cloud becomes, the faster it rotates. Think about a figure skater pulling in their arms. The skater does not add energy. They shrink their radius. The spin accelerates on its own. The same principle scales up to an object the size of an early solar system. Now the collapse becomes asymmetric. And this is the crucial point. Along the spin axis, the direction we would call north and south of the rotating cloud, there is no rotational support. Nothing is pushing material outward in that direction. Gravity is pulling everything inward, and nothing resists it. So in that direction, the collapse is free. The cloud falls toward its own equatorial plane quickly, unimpeded. But in the equatorial direction, the direction around the spin axis, the rotation is pushing material outward the way a spinning pizza dough resists being pressed flat. The centrifugal effect of the rotation counteracts the inward pull of gravity. The collapse in that direction stalls. It slows. It cannot proceed nearly as freely as the pole-to-pole collapse. The result is inevitable. The north-south direction collapses. The equatorial direction holds. A roughly spherical cloud of gas and dust, over hundreds of thousands of years, becomes a disk. Not a roughly flat structure, not approximately disk-like. A true disk, thin relative to its width in a ratio that makes a sheet of paper look thick by comparison. A young sun forms at the center, drawing the vast majority of the cloud's mass into a hot, dense core. The remaining material, about 1% of the total, spreads out in the surrounding plane. That remaining 1% is the protoplanetary disk, the rotating sheet of gas and dust from which everything we call the solar system eventually assembles. Within the disk, temperature and chemistry begin to sort the material. Close to the young sun, the heat is too intense for volatile compounds like water and methane to survive in solid form. Only rocks, metals, and silicates condense. Farther out, beyond a boundary astronomers call the frost line, temperatures drop enough that ices can persist, and the outer planets assemble with access to far more raw material than the inner rocky worlds. The planets that form in this plane inherit the plane. They do not choose their orbits. The geometry of the disk is stamped into them from the beginning, and anything that wanders too far above or below the plane, a stray chunk of rock, a rogue body that was knocked off course by an early collision, faces the disk's own gravity pulling it back, or encounters a scattering event that sweeps it out toward the far reaches of the solar system. The original protoplanetary disk is long gone. The young sun's radiation pressure and outflowing particles, what we now call the solar wind, gradually dispersed the remaining gas. The disk dissolved, in a cosmic sense, within the first 10 million years or so, but the planets it left behind held their positions in the plane it had defined. The geometry was already locked in. The disk persisted as a memory even after the disk itself vanished. This is what makes the flatness a fossil. The original rotating cloud no longer exists. The protoplanetary disk no longer exists. But the planetary plane remains, carrying the rotation signature of that early cloud, the way a bone carries the shape of the animal that built it. We can look at the solar system's geometry today and read backwards to the physical conditions of its birth 4.5 billion years ago. And the solar system is not alone in this. Flatness is the natural outcome whenever gravity and rotation coexist at any scale. Saturn's rings are a disk so thin relative to its width that if you scaled Saturn's ring system to the width of a standard sheet of paper, the rings would be thinner than the paper itself. The Milky Way is a disk, 100,000 light years across, and only about 1,000 light years thick through most of its span. Look at any galaxy in a long exposure photograph, and you are looking at gravity plus rotation producing flatness at a scale 1 trillion times larger than our solar system. Look at the swirling material falling into a black hole, and you will see it organizing itself into an accretion disk. Flat, fast-moving, inevitable. Flatness is not coincidence. Flatness is what physics makes. A spherical solar system with orbits spread equally in every direction like spokes of a globe would not be the natural state. It would be the strange thing. It would require an explanation. The disk requires no explanation. It is what rotation and gravity produce. Every time. At every scale. Without exception. But knowing the disk is flat and knowing how to use that flatness as a navigation tool are two entirely different problems. And the geometry the disk created turns out to be more precisely defined than most people realize. That geometry is more precise than it first appears. Astronomers gave it a formal name, the invariable plane. Not simply the average of where the planets orbit, but a weighted average, calculated by giving more influence to bodies with more angular momentum. The plane is defined by the combined rotational weight of everything circling the Sun. And one planet outweighs all the others combined in that calculation. Jupiter. Massive enough to bend the average toward itself. Massive enough that its orbit and the invariable plane nearly coincide. Think about what that means in practice. Earth's orbit deviates from the invariable plane by only about 1.5 degrees. That is nearly nothing. A tilt you would barely detect by eye on a diagram. Mercury sits tilted about 7 degrees from the ecliptic. Its orbit noticeably inclined compared to its neighbors. Venus, Mars, and the gas giants all stay within a few degrees. The system is tightly layered, like a deck of cards fanned only slightly. Then, there is Pluto. Pluto tilts about 17 degrees from the ecliptic. Its orbit rises visibly above and below the band where the planets travel. And beyond Pluto, a handful of small icy bodies tilt more steeply still, their orbits cutting across the plane at sharp angles. Long-period comets arrive from almost any direction, plunging down through the disk from above or rising through it from below, shedding ice and gas as they near the Sun, then retreating back to the outer reaches. These are the outliers. They are decorations on a fundamentally flat system. The architecture beneath them, the real structure, lies in that thin orbital band close to the invariable plane. The picture did not hold. The original protoplanetary disk dispersed billions of years ago. The dense cloud of gas and dust that built the planets was swept away by the young sun's radiation within the first few million years of the solar system's life. Nothing of that original disk should remain. And yet the disk is still there. Not as gas, not as dense cloud, as dust. It never entirely went away. The dust disk that exists today is not a remnant of the original cloud. It is freshly generated, continuously, by processes still happening now. In the belt between Mars and Jupiter, asteroids collide. Not gently. When two rocky bodies meet at orbital speeds, the collision grinds them down to fragments, and the fragments to grains, and the grains to powder. Comets passing near the Sun shed dust along their orbits as their ice sublimates, releasing embedded particles into space. Icy bodies far beyond Neptune erode slowly, shedding fine grains over long stretches of time. All of these sources sit in the plane. All of the dust they produce falls under the influence of the Sun's radiation pressure and the gravitational tugs of the planets. It settles. It stays. The plane reasserts itself through the material. The result is a thin, faintly luminous disk of fine dust still tracing the geometry of the solar system today. And on a sufficiently clear night, far enough from city light, you can see it. It rises after sunset as a soft cone of pale light, tilting up from the horizon along the ecliptic. Before sunrise, it stretches upward in the opposite direction. It is not an atmospheric glow, not an aurora, not any artifact of weather or pollution. It is sunlight, scattered back toward Earth by trillions of dust grains, arrayed in the plane of the solar system. Astronomers call it the zodiacal light, named for the constellations of the zodiac that lie along the ecliptic band. To see the zodiacal light is to see the disk itself with the naked eye. The geometry you have been trying to picture, The thin, flat structure that encodes the rotation of the original cloud is present in the sky tonight, visible without a telescope if you know where and when to look. The dust cloud is densest near the sun and thins moving outward. A somewhat brighter band, called the asteroid belt dust band, marks the particular contribution from collisions in the main belt between Mars and Jupiter. A fainter outer contribution comes from the grinding of icy bodies beyond Neptune. Seen from far above, the whole system would appear as a wide, shallow sheet of diffuse light, with the planets threading slowly through it. Inner regions bright, outer regions dimming gradually into darkness. But the dust disk does more than glow, it also obscures, not uniformly, not in all directions, in one direction specifically. When you look outward along the plane, your line of sight passes through the full depth of the dust cloud. Sunlight scattered by those grains drowns faint signals from the universe beyond. The more you look along the plane, the more dust you look through. Looking straight up, perpendicular to the plane, your line of sight crosses the thinnest possible slice of that cloud. Almost no dust, almost no scattered light. The sky directly above the solar system's north pole and below its south pole offers something the rest of the sky cannot: the cleanest possible view of the universe from inside our disk. The same structure that built our world also crowds our window onto everything beyond it. Now, zoom outward once more. The solar disk is not the only disk in play. Watch Venus low in the western sky after sunset sometime, orange and steady, just above the horizon. Then find Jupiter on the same night. It will lie along the same narrow arc of sky. Wait a few days, and the moon crosses that same band. These objects do not share the sky by accident. They share a plane. They trace the ecliptic. The arc they follow is the solar system's disk, projected onto the sphere of the night sky, tilted at its characteristic angle to the celestial equator. Astronomers use two different coordinate systems for locating objects in the sky. One is tied to Earth's equator, projected outward to form the celestial equator. One is tied to the ecliptic, the plane of Earth's orbit. These two systems are tilted about 23.5 degrees relative to each other. That tilt is not arbitrary. It is Earth's axial tilt, the same geometry that gives the northern hemisphere its summer when it leans toward the sun and its winter when it leans away. The ecliptic and the celestial equator cross in two places, which mark the spring and autumn equinoxes, the days when day and night run equal. But the solar disk, as precise and flat as it is, sits inside a structure enormously larger than itself, and that structure is tilted sharply relative to our own. The Milky Way is a slowly spinning spiral hundreds of thousands of light years wide. It contains several 100 billion stars, woven together with gas, dust, and dark matter. It is, at the scales that govern its shape, just another disk. Gravity plus rotation flattened it over billions of years, the same principle that flattened the solar system. The same principle at work in Saturn's rings and accretion disks around black holes. But the galactic disk and the solar disk are not aligned, not close to aligned, not approximately the same orientation. They are tilted by roughly 60 degrees relative to each other. The Sun and its planets orbit the galactic center in their own private plane, tipped sharply against the plane of the galaxy. From Earth, the Milky Way's band cuts across the night sky at a pronounced angle to the ecliptic. The galactic bulge, the bright, crowded heart of the galaxy, rises high for observers in the southern hemisphere during certain months, nowhere near the direction the ecliptic follows. The two great disks intersect, but they do not agree. Think about what you would see from a vantage directly above the sun's north pole. The galactic band would not lie where Earth's night sky places it. The bulge would appear in a different direction relative to the ecliptic. The patterns you recognize from standing on Earth would look like the same stars, the same constellation shapes, but arranged in an unfamiliar orientation. The Milky Way arcing through an unexpected part of the sky. The geometry you have spent a lifetime taking for granted would feel wrong without being wrong. Same universe, different angle. The sun is also moving. Relative to the nearby stars, it drifts at roughly 200 kilometers per second toward a region of sky in the constellation Hercules. It has been carrying its planets through that drift for the entire history of the solar system, threading slowly through the galaxy's structure over millions of years. And right now, the Sun sits inside a roughly elongated region of low-density interstellar gas called the local bubble, a cavity carved by ancient supernova explosions. The local bubble's walls are uneven. Some directions open more cleanly into the wider galaxy. Others press closer. The same disk geometry that defines the solar system, the same flatness that gave us the invariable plane and the zodiacal light, is embedded within a galaxy that maintains its own orientation and its own local structure, none of which had any obligation to align with ours. We live at the intersection of multiple flatnesses, multiple disks, nested, tilted, each carrying the signature of its own rotation. None of them parallel, none of them coincidental. And what lies along those disks, what populates the plane and what gets filtered by it, turns out to be one of the more useful facts in all of observational astronomy. And all of that, the nested disks, the tilted planes, the local bubble pressing in from different directions, exists before a single rocket ever leaves the ground. Come back closer now, all the way back, past the galactic drift, past the zodiacal dust, past the orbit of the outermost planets, back to Earth, back to the ground beneath you. You are sitting still. That is what it feels like. The floor is solid, the walls are not moving, the air in the room is not rushing past you in any particular direction. Every sensation you have tells you that you are at rest. But you are not at rest. Not even close. Right now, this moment, you are moving sideways through space at roughly 30 kilometers per second. Not you personally, not your body relative to the room, but your body, the room, the building around it, the bedrock beneath the building, the oceans, the mantle, the molten iron at Earth's core, the entire planet, all of it moving together along Earth's orbit around the Sun, 30 kilometers every second, 1,800 kilometers every minute, more than 100,000 kilometers every hour. You do not feel it because everything moves together. There is no wind. There is no jolt. The motion is so steady, so perfectly shared by every atom around you, that it registers as nothing at all. This is the most important mechanical fact in the entire story of space travel, and it is almost never stated plainly. Think about what this means for a rocket sitting on a launch pad. Before its engines fire, before a single gram of propellant burns, that rocket is already moving through the solar system at 30 kilometers per second. It inherited that motion the moment it was built. The steel in its frame, the fuel in its tanks, the payload at its tip, all of it swept sideways around the Sun at the same steady pace as everything else on Earth. Here's what most people assume: that a rocket must work hard to reach orbital velocity, that it starts from rest and climbs, engine screaming, until it has built up enough speed to stay aloft. That reaching orbit is the hard part. But something was wrong. The rocket does not build orbital velocity from scratch. It inherits most of it for free. When the engines fire and the rocket climbs away from the launch pad, it carries its 30 kilometers per second of sideways solar orbital motion with it. To reach low Earth orbit, it needs to add only about 8 kilometers per second relative to Earth's surface. Not 30, not 38, 8. The rest was already there, already paid for, delivered by the simple fact that the rocket existed on a moving planet. To travel to the moon, the additional cost beyond Earth orbit is modest. To send a probe toward Mars, modest again. To reach Jupiter, still working from the same inherited starting point. Every destination in the solar system that lies roughly within the plane of the planets is, in a sense, downstream. The rocket nudges an orbit that is already partway to where it needs to go. Nothing the rocket does cancels its sideways solar orbital motion. There is no engine maneuver, no trajectory tweak, no burn of any duration that returns the spacecraft to rest, with respect to the Sun. The motion is inherited, and it stays inherited. That is why almost every spacecraft in history, from the earliest probes of the 1950s to the most sophisticated interplanetary missions launched in recent decades, has ended up traveling within or very close to the plane of the planets. Not because mission planners preferred it, because there was almost no other option. The plane is not a road, it is a current. Everything in it is being carried along, and a spacecraft launching from Earth is born already inside that current, already flowing with it. Now think about what happens if a mission wants to leave the current, not travel along it, not even cut across it at a shallow angle. Leave it entirely, rise above it, aim for the polar regions of the solar system, the unexplored space directly above and below the sun. This is where the inheritance becomes a trap. To rise above the ecliptic, a spacecraft cannot simply point upward and fire its engines. Pointing upward changes where the thrust goes, but the 30 kilometers per second of sideways motion is still there, still carrying the spacecraft along in the plane. The spacecraft will arc upward for a time, then curve back, because the inherited velocity keeps pulling the trajectory sideways. To truly leave the plane, the spacecraft must first erase what it inherited. It must cancel 30 kilometers per second of sideways motion, completely, and then replace it with 30 kilometers per second of motion in the perpendicular direction, straight up, relative to the disk. Not reduce it, not partially cancel it, erase it entirely, and rebuild in a new direction. That is an enormous cost. It is not the cost of climbing a gravity well. It is not the cost of traveling a long distance. It is the cost of changing the fundamental direction of a fast-moving object. And 30 kilometers per second is not slow. It is faster than any rocket in history has been able to provide as a course correction once a spacecraft is already in flight. Up feels like the natural direction of escape. Away from the ground, away from gravity, out into open space. Every instinct says that up is freedom. Up is, in fact, the hardest direction in the solar system. The hardest not because of what lies above, but because of what lies below. Built into every kilogram of mass on every launch pad on Earth. The inheritance that makes horizontal travel cheap makes vertical travel almost prohibitively expensive. The plane is a current, and the most costly thing you can do in a current is try to leave it at a right angle. The spacecraft that have managed to climb toward the solar poles did not do it by pointing upward and burning. They did it through a different method entirely. A method that takes years, requires precise timing, and uses the planets themselves as tools. Let's give that current a number then, and see what it would actually cost to push through it. Mission designers have a term for this cost. They call it delta V. The phrase means change in velocity. It is the total amount of speed a spacecraft can add, subtract, or redirect using its onboard fuel. Think of it as a lifetime budget. Every maneuver draws from it. Once it is spent, the spacecraft goes where physics sends it. No more corrections, no more adjustments. The budget is fixed from the moment the rocket leaves the ground, set by two things: how much fuel it carries, and how efficiently the engines burn that fuel. Chemical rockets have been refined for roughly 70 years now. Decades of engineering, iteration, and incremental improvement. They are extraordinarily capable machines, and they have a ceiling. Fuel chemistry sets a hard limit on how much delta V a given mass of propellant can provide. Engineers have pushed that ceiling as high as it will go. It does not move much anymore. Here is what that ceiling allows. Reaching low Earth orbit from the surface costs roughly 9 to 10 kilometers per second of delta V. Most of that is fighting gravity and atmospheric drag, and building the sideways speed needed to stay in orbit. From there, leaving Earth's orbit entirely and heading toward the Moon costs another 3 to 4 kilometers per second. A transfer to Mars, on a standard low-energy trajectory timed to a favorable launch window, costs about 4 kilometers per second beyond Earth orbit. A transfer all the way to Jupiter, which requires crossing the asteroid belt and entering the outer solar system, costs roughly 6.5 kilometers per second beyond Earth orbit. These are large numbers, and every one of them is within the reach of modern rockets. Pluto sits at the outer edge of the solar system, nearly 50 times farther from the Sun than Earth is. Sending a spacecraft to Pluto is one of the most demanding missions humanity has ever attempted. The New Horizons probe, launched in 2006, was the fastest spacecraft ever sent toward a destination at that point in history. It crossed the orbit of the moon in just 9 hours, and it cost less delta phi than pointing a spacecraft directly upward out of the plane. That is not a slight difference, not a marginal one. Reaching an icy world at the frozen edge of the solar system is easier, in the formal currency of mission design, than sending the same spacecraft perpendicular to the planetary disk to a height no greater than Earth's own orbital distance from the Sun. Think about what that means. Not reaching Pluto and then climbing out of the plane, just climbing out of the plane to a height that does not even exceed Earth's orbit. That journey is more expensive. The reason is the 30 kilometers per second. A spacecraft sitting in low Earth orbit is already moving sideways at roughly 30 kilometers per second, carried along by the motion inherited from the planet that launched it. That motion runs parallel to the planetary plane, as it always has, as it always will, for anything born on Earth. To leave the plane on a truly vertical trajectory, the spacecraft must first erase that sideways motion, all of it, and then it must build the same amount of motion again, but now pointing perpendicular to the plane instead. The total cost of that maneuver is roughly 30 kilometers per second of delta phi from low Earth orbit. 30, not 10, not 15, 30. The largest interplanetary missions ever flown across all of spaceflight history have delivered total delta V budgets in the range of 15 to 20 kilometers per second across their full working lifetimes. And most of that budget was spent slowing down at destinations, adjusting trajectories, and correcting errors accumulated over years of flight, not accelerating, slowing. No chemical rocket has ever delivered 30 kilometers per second to a single spacecraft. Not once, not even close. Direct vertical departure from the solar system is not a mission profile that is difficult to execute. It is a mission profile that does not exist. It has never existed. It cannot exist using any engine technology humanity has currently built or flown. The answer was stranger than expected. Because the reason is not about distance. It is not about how far the sun's poles are. They are roughly the same distance from Earth as the rest of the sun. The poles are not remote in the ordinary sense of that word. They are remote in a purely mechanical sense, a consequence of geometry and inherited motion. Going outward, toward Jupiter or Saturn or Pluto, a spacecraft adds velocity along the direction it is already moving. The existing 30 kilometers per second is not wasted. It is the foundation. The engine adds a modest push on top of it, and the resulting trajectory stretches into a long ellipse that reaches farther and farther from the sun. The sun's gravity is there the entire time, curving the path, exchanging speed for altitude and altitude for speed, doing enormous amounts of work for free. The spacecraft rides that exchange all the way to the outer solar system. Going upward, perpendicular to the plane, none of that applies. The existing 30 kilometers per second points the wrong direction. It cannot be redirected gradually. It cannot be partially used. It simply costs what it costs to cancel it and replace it. The sun's gravity, meanwhile, does not help. The sun pulls inward toward itself, not downward relative to the plane. A spacecraft climbing perpendicular to the plane is climbing along a direction the sun's gravity does not care about. Every single kilometer per second of vertical velocity must be purchased with fuel. There is no discount. There is no assistance. The bill is paid in full. This is why the sun's polar regions are, in the formal language of mission planning, the most remote destination in the solar system. Not the outer edge of the Oort cloud, not the space between the stars. The empty sky directly above the sun, at a distance no greater than Earth's own orbit, is harder to reach than Pluto. Distance, it turns out, is not the right way to measure remoteness. Delta V is, and by that measure, the ceiling above the solar system is a wall that no rocket has ever climbed. The spacecraft that have managed to angle their trajectories toward the solar poles found a way around the wall, not through it. The spacecraft that have managed it found a way around the wall, and that way has a name. It is called a gravity assist, a planetary flyby, a swing-by. The names vary. The principle does not. Here is what it means. A spacecraft on a carefully chosen path flies past a planet. As it approaches, the planet's gravity pulls it closer, accelerating it. As it departs on the far side, the planet's gravity pulls it back, decelerating it. In isolation, those two effects cancel. The spacecraft arrives with a certain speed and leaves with the same speed relative to the planet. Nothing gained, nothing lost. That would be the end of the story. Except the planet is not sitting still. The planet is moving. It is in orbit around the sun, traveling at its own velocity, carrying its gravitational field with it like a moving hook. And a spacecraft that swings through that moving field does not return to where it started. It leaves the encounter with a different speed relative to the sun. Not a small difference. Several kilometers per second per encounter, depending on how the geometry is arranged. The spacecraft borrows a tiny fraction of the planet's orbital energy. The planet loses an immeasurably small amount of its own. Energy is conserved. Momentum is conserved. Every law of physics is satisfied, and the spacecraft goes somewhere it could never have reached on fuel alone. It is the closest thing in physics to a free lunch, but the geometry is not free. That is the part that costs. The spacecraft must arrive at the planet at exactly the right time. It must approach from exactly the right angle. It must depart on exactly the trajectory the mission requires. Get any of those wrong, and the planet's gravity redirects the spacecraft somewhere useless, or nowhere in particular, with no way to correct the error later. The launch window is narrow. The trajectory is locked in years before the spacecraft leaves the ground. Mission designers have perhaps one shot, and they spend years of computation earning that shot before a single bolt is tightened on the vehicle. The delta V cost of the flyby itself is essentially zero. The cost in planning is enormous. Heavier planets give larger boosts. Faster approaches give larger redirects. Approach angle determines whether the borrowed energy adds to the spacecraft's speed, subtracts from it, or bends its direction sideways. Trajectory designers can chain these encounters together, shaping paths in ways that pure rocket fuel could never afford. And for missions trying to leave the plane of the solar system, that chaining is not a convenience. It is the only option available. Jupiter is where the real power lives. It is the most massive planet in the solar system, and, by a wide margin, the most powerful natural slingshot we have. A close flyby of Jupiter can change a spacecraft's speed by 10 kilometers per second or more in a single pass. Think about what that means. The entire delta V budget of a modest interplanetary mission, delivered in one encounter, without burning a gram of fuel. And with the right approach geometry, Jupiter does not just accelerate a spacecraft along the plane, it can throw one entirely out of the plane, it can redirect motion sharply upward or downward relative to the ecliptic, bending a trajectory that would otherwise skim along the planetary disk into something that climbs steeply away from it. Jupiter is the ladder that reaches high enough, but Jupiter is not always available. The planet is where the planet is. If the geometry is wrong, if the launch window does not align, if the mission cannot wait for the alignment to come around, another approach exists. Slower, more patient, no less effective. Venus is small compared to Jupiter. A Venus flyby delivers a much more modest inclination change per pass, but Venus is close. It orbits relatively quickly. A spacecraft can be designed to loop between an inner orbit and Venus repeatedly, using each pass to accumulate a little more tilt. The technical term for that tilt is inclination, the angle between an orbit and the reference plane. Each Venus flyby adds a small increment of inclination, not enough to notice in isolation, but the encounters stack. One pass, then another, over years of patient looping. The spacecraft climbs gradually out of the ecliptic, not in a single dramatic leap, but in a long, slow accumulation of borrowed geometry. Patience costs nothing in delta Phi. The spacecraft pays in years of mission lifetime rather than tons of fuel. This is the deeper principle the two planets illustrate. The universe rewards staying in the disk. Everything in the plane moves at compatible speeds, in compatible directions. Gravity works with you. Orbits connect naturally, but nothing forbids escape from the plane. No physical law prevents it. The penalty is not impossibility. The penalty is cost, and that cost is higher than rockets alone can pay in a single straight ascent. Planets used as ladders are how the debt gets settled. Every spacecraft that has ever climbed out of the plane has done it by trading time and complexity for the missing delta V. A decades-long gravity assist era, roughly 60 years now, built on exactly this logic. Neither route is simple. Jupiter demands perfect timing and offers one chance. Venus demands years and offers many chances, each one small, but both routes share the same essential character. The spacecraft does not fight the geometry of the solar system, it borrows from it. The missions that have pointed themselves toward the solar poles understood this. They each carry the record of a trajectory that someone spent years computing, built around one or more planetary encounters, designed to accumulate the inclination that no rocket could have provided directly. The details of those missions are worth looking at closely, because each one solved the problem differently. The details of those missions are worth looking at. But before we go there, set the trajectories aside for a moment. Put down the delta V budgets and the gravity assist windows and the years of computation, because none of that matters until you understand what the destination actually is. What is up there, above the plane, at the poles of the sun? What have we been working so hard to reach? The answer is stranger than most people expect. For centuries, human beings have studied the sun. They have tracked its spots, measured its radiation, watched its corona bloom during eclipses, mapped the slow drift of its magnetic features across the face of the star. The 11-year solar cycle, the rhythm of sunspot maxima and minima, the great storms of charged particles that occasionally sweep past Earth and disrupt satellites and power grids. All of it, painstakingly documented. All of it studied in extraordinary detail. Here is what almost none of that science had access to: the poles. Think about what that means in practice. Earth orbits the sun in the same plane as the other planets. Every spacecraft ever built has traveled in that plane, or close to it, which means every telescope, every probe, every solar observatory has watched the sun from the same narrow band around its equator. Sunspots occur near the equator. Flares erupt from equatorial latitudes. The 11-year cycle is tracked through equatorial features. Eclipse studies reveal the equatorial corona, the entire accumulated archive of solar science, centuries deep, is essentially equatorial science. The poles, where the sun's axis of rotation meets its surface, are almost entirely invisible from this vantage, not partially obscured, not underrepresented, invisible in any useful sense. Even at the most favorable geometry, as Earth moves slightly above and below the sun's equatorial plane during the year, the poles appear foreshortened. Seen at a shallow grazing angle, they are lost in projection across the curved face of the star. You're looking across the surface at an angle so steep that the polar regions compress into a thin sliver at the edge of the disk. The detail you need is gone. The geometry swallows it. But the reality was different, because the poles are not the quiet, featureless edges they appear to be from the equatorial plane. They are not peripheral regions where interesting behavior dies away. They are where the sun's most fundamental processes are rooted. The first of those processes is the solar wind itself. The sun continuously sheds material into space. Hot ionized gas, a stream of charged particles flowing outward in all directions, filling the heliosphere, the vast bubble of solar influence that extends far beyond the outer planets. Earth moves through this wind constantly. It shapes the magnetic environment of the entire solar system. Scientists have known about the solar wind for decades. What they did not fully appreciate until observations could reach the polar regions is that there are two solar winds, not one, two, and they are fundamentally different from each other. The fast solar wind flows outward at roughly 700 to 800 kilometers per second. That is not a measurement of how fast it eventually reaches those speeds. That is its cruising speed, nearly twice the velocity of its companion. The fast wind is also chemically distinct. The ratios of elements and the ionization states of those elements, the degree to which atoms have been stripped of electrons by heat and radiation, are different from what you find in the slower flow. The fast wind carries the signature of different formation conditions, different temperatures, different pressures, different physical environments at its source. That source is the poles. To understand why, you need to understand what a coronal hole is. The Sun's outer atmosphere, the corona, is a region of extraordinarily hot, thin plasma where magnetic field lines thread through the gas. In most places, those field lines loop. They rise from the surface, curve outward into space, and return to the surface somewhere else, forming closed arches. The plasma trapped in these closed loops cannot easily escape. It is held in place, caught in a magnetic cage. But in some regions of the corona, the field lines do not loop back. They open outward into space, reaching away from the sun without returning. These are coronal holes, regions where the magnetic geometry provides an exit. The plasma there is thinner, less dense than in the surrounding closed-loop regions, because it is not being held. It flows outward along the open field lines, unimpeded, streaming away from the sun at high speed. In ultraviolet images, coronal holes appear as dark patches on the sun's face. Not dark because they're cold, not dark because something is blocking them. Dark simply because they are thinner. Less plasma means less emission. Less emission means darker. The word is a description of what the images show, not of what the region is. During the quiet phases of the 11-year solar cycle, the phases astronomers call solar minimum, persistent coronal holes settle over both polar regions of the sun. Not temporary structures, not brief openings, large, stable formations that can persist for years without significant change. The polar coronal holes are where the fast solar wind originates. The slow solar wind is a different creature. It moves at roughly 300 to 500 kilometers per second, half the speed or less of the fast wind. It is more turbulent. Its density varies more from moment to moment. Its composition is less uniform. It originates not from the stable interior of polar coronal holes, but from their edges, and from a region near the sun's equator called the streamer belt, where the sun's magnetic field forms bright looping structures visible during total solar eclipses as long white arches extending from the solar disk. Both winds exist simultaneously in the heliosphere. They flow outward together, occupying different regions of space, alternating past Earth as the sun rotates, and the different source regions sweep past. The fast polar wind and the slow equatorial wind. Two streams with different speeds, different compositions, different origins, passing Earth in sequence, shaping the space environment in distinct ways depending on which stream is arriving. The second fundamental polar process is the global magnetic field reversal. Every 11 years, roughly synchronized with the solar cycle's maximum, the sun's entire large-scale magnetic field flips. North becomes south, south becomes north. The reversal originates at the poles, propagates through the solar interior, and reshapes the structure of the heliosphere across billions of kilometers. Every large-scale magnetic phenomenon in the solar system, the configuration of the heliospheric current sheet, the behavior of galactic cosmic rays as they travel inward toward Earth, the protection the sun's field provides against radiation from outside the solar system, all of it resets when the poles reverse, and the process begins at the poles, where observation was almost impossible for most of solar science history. This is what the equatorial archive had been missing. Not peripheral details, the engine room. There is a useful way to think about this. Imagine you are trying to understand the weather of a city by watching only the roads. You observe which roads are flooded, which are windy, which are dry. You build a detailed picture of road conditions. You track patterns. You construct a calendar of when conditions change. All of that data is real. All of it is accurate. But you have never once looked at the sky. You have never observed the weather systems that determine road conditions. You have been studying the visible consequences of processes you cannot directly see. That is, roughly, the situation solar science found itself in for most of its history. The poles are the sky. The equatorial observations are the road conditions. To miss the poles is to study symptoms while missing the source. The biggest surprises were still ahead, because knowing what the poles do is one thing. Observing them directly, in detail, over a full solar cycle is another. And the history of the missions that actually achieved that view is a story of engineering choices forced by exactly the physics we have been discussing. Stay with that contrast a moment longer. Fast wind from above, slow wind from the equator, two streams, two speeds, flowing side by side through the heliosphere as the sun turns. The question worth asking is what happens at the seam between them. The answer is one of the most remarkable structures in the solar system, and almost no one has heard of it. Where the fast polar wind meets the slow equatorial wind, the sun's magnetic field does not simply smooth out and blend. It forms a boundary, a thin physical surface separating two regions of opposite magnetic polarity, north on one side, south on the other. As the sun rotates, that boundary does not stay flat. It warps, it ripples, it twists outward through the entire heliosphere in a long, slowly turning spiral that stretches past all the planets and reaches into the outer solar system. Scientists call it the heliospheric current sheet. It is the largest single magnetic structure in the solar system. The common description for its shape is the ballerina skirt. The image earns its name. As the sun spins, the sheet's hem rises and falls relative to the solar equator, sweeping in a slow, regular rhythm across the space between the planets. Seen from a great distance above, it would be one of the most striking sights in the solar system. A slowly spinning, slowly warping magnetic membrane, huge and intricate, undulating like a skirt's edge with each rotation. The planets thread through it. Earth crosses it several times during each solar rotation. Every crossing produces small, measurable changes in the magnetic environment around our planet. During more active periods, those crossings can contribute to mild geomagnetic disturbances at the surface. But here is where it gets strange. No one has ever actually seen this structure directly. Not once. No direct image of the heliospheric current sheet has ever been made. Its shape is inferred. Scientists map it indirectly, by measuring changes in the magnetic field as spacecraft pass through it, and by observing the corona from the ground during eclipses, where visible streamer structures hint at the sheet's likely geometry in the plane below. What the sheet actually looks like in 3 dimensions, at different phases of the solar cycle, in its full geometry, is still inferred rather than observed. A view from above would resolve for the first time what its true shape actually is. The sheet's geometry is not fixed. It breathes with the solar cycle. Near solar minimum, when the sun is quietest, the sheet lies nearly flat along the solar equator. The ripples are gentle. The peaks and troughs stay close to the equatorial plane. Near solar maximum, as activity builds, the sheet tilts steeply. Its peaks and troughs climb far from the equator. The hem of the skirt rises and falls dramatically with every rotation, sweeping past the planets at extreme angles. The sheet becomes one of the visible expressions of the sun's most disordered, most energetic phase. Which brings the question, what drives the cycle that shapes it? Roughly every 11 years, the sun's magnetic field reverses. What was the north magnetic pole becomes the south becomes the north. This is half of a full 22-year magnetic cycle, sometimes called the Hale cycle, after the astronomer who first identified the polarity pattern in sunspot pairs. The reversal appears to drive much of what we observe at the surface. Sunspot numbers, flare frequency and strength, corona structure, the size and behavior of polar coronal holes, the tilt of the heliospheric current sheet itself. All of it rises and falls with this deeper magnetic rhythm. The reversal does not happen all at once. It is not a sudden flip. The process is gradual and it takes most of the 11-year cycle to complete. It begins at the poles. Throughout each cycle, sunspots and active regions form in pairs. The 2 spots in each pair carry opposite magnetic polarities. One leads across the face of the sun as the sun rotates, the other trails behind. Across the entire sun, the leading spots of each hemisphere share a common polarity. The trailing spots share the opposite one. Over years, as active regions decay, the trailing polarity does not simply disappear. It diffuses and drifts poleward. Slowly, incrementally, magnetic flux of the opposite polarity migrates toward the poles, like debris drifting toward a drain, accumulating year after year. When enough opposite polarity flux has gathered near a pole, it cancels the existing polar field. The polarity flips, not abruptly, not cleanly, gradually and incompletely. The two poles do not reverse at the same time. One can lead the other by months or even years. During those intervals, the sun's global magnetic structure shifts from a simple dipole, two poles, into something stranger, a quadrupole. Multiple magnetic poles at unusual latitudes, the geometry temporarily complex until the second pole catches up, and the sun settles back into a clean, reversed dipole. The asymmetry resolves. The cycle continues. And here is the part that reframes the entire story of solar cycles. The strength of the polar magnetic field at the end of one cycle appears to predict the intensity of the next. A strong polar field at the close of one 11-year cycle generally precedes a strong sunspot cycle 11 years later. A weak polar field precedes a weak one. The precise mechanism connecting polar field strength to future cycle intensity is still being worked out. The full causal chain is not yet understood, but the correlation is strong enough that astronomers now use polar field measurements as one of their more reliable forecasts of upcoming solar activity. Think about what that means. The visible surface of the sun, with all its activity, its sunspots and flares and erupting plasma, is the result. The cause lives at the poles, at latitudes that face nearly edge-on from Earth, at latitudes that are foreshortened, projected, compressed by viewing geometry into near invisibility for any observer locked inside the planetary plane. The poles are not the quiet ends of the sun. They are the dynamo room. Activity at the equator is a consequence of processes that play out over years at latitudes we have barely been able to see. The heliospheric current sheet, vast enough to wrap the entire solar system, is shaped by those poles. The 11-year cycle is driven by those poles. The forecast for the next cycle is written in the polar field strength of this one. For most of solar science history, that room was closed. What it would take to open it, to actually observe the poles in detail across a full solar cycle, was a mission challenge defined entirely by the physics we have been discussing. The same inherited velocity, the same delta V wall, the same need to borrow from solar system geometry rather than fight it. The missions that answered that challenge did not go the obvious way. They went the only way that physics allowed. Let's go closer now, all the way down to the surface itself. The sun you picture when you close your eyes is probably smooth, a uniform sphere of light, undifferentiated from pole to equator. That picture is accurate enough for most purposes, but it is not the whole picture, and the poles tell a different story than the equator does. Near the equator, the magnetic field organizes itself into broad structures, sunspot groups, active regions, wide complexes of looping field lines arcing thousands of kilometers above the surface. These are the features that dominate solar imagery. These are the features that centuries of observation have catalogued in detail. But at the poles, the field does something different. It does not gather into large organized forms. It breaks apart. Countless small concentrations of magnetic flux, each one modest in size, weave into a fine tangled network across the polar surface. No broad active regions, no large sunspot groups. A texture finer and more intricate than anything the equatorial surface produces. Above this network, the field threads upward in small bundles. Each bundle marks where a concentration of flux has worked its way out of the convective layer and into the corona above. And from those bundles, something remarkable forms. Polar plumes. They are long, thin streams of plasma extending outward from the polar regions, like grass blades aligned with the open magnetic field lines. Each one is a thin column of slightly denser plasma, threading through the surrounding fast solar wind. From inside the planetary plane, during a total solar eclipse when the bright disk is hidden and the fainter corona becomes visible, they appear as faint rays curving away from the sun's polar limbs. Easy to overlook, easy to mistake for a trick of the light. Something else was happening. The view from inside the plane is almost exactly the wrong perspective for understanding what polar plumes actually are. To see them properly, you would need to be above, looking down along the rotation axis. Imagine that view. The familiar dark equatorial sunspot groups have vanished. In their place, a quiet granular surface stretches out below, threaded with those delicate bundles of magnetic flux. And from the pole, radiating outward in every direction along the open field lines, the plumes spread like the petals of a slowly spinning flower. Brilliant fast wind streams away in long straight rays. The sun does not look like a furnace from that angle, not a violent, erupting engine, less like a star and more like the open eye of something patient and very old. The plumes form the visible texture of the polar corona during eclipses. They also carry the compositional signature of their origin. The fast wind escaping through open polar field lines more closely resembles the underlying solar photosphere than the slow wind does. The slow wind, originating from closed-loop coronal regions at lower latitudes, has spent longer in residence in the corona, and certain elements are preferentially enhanced by that prolonged exposure. The fast wind escapes more directly and carries less of that processing. The differences are subtle but measurable. Astronomers can take a parcel of solar wind arriving at Earth and trace it back to its source, fast polar hole or slow equatorial streamer belt, by reading its chemical composition. Now comes the question of memory. The solar cycle does not proceed at the same intensity every time. Some cycles are stronger than others. Some produce many large sunspot groups and frequent powerful flares. Others are quiet, and there are periods far longer than a single cycle, lasting decades or even centuries, when solar activity drops markedly and stays low. These extended quiet periods appear connected to weaknesses in the polar field, sustained over many cycles. When the poles fail to accumulate strong flux from one cycle to the next, the whole cycle that follows runs weaker. When that weakness persists across multiple reversals, activity can drop and stay low for a very long time. The polar field does not just shape the next cycle, it is the long-term memory of the sun. The geometry of activity across the cycle also reflects polar influence. Large filaments and prominences tend to align with boundaries between regions of opposite magnetic polarity. As flux migrates poleward through the cycle, those boundaries shift latitude, and the locations of major eruptions shift with them. Chart the latitude of sunspot groups across many successive cycles, and a pattern emerges. Sunspot bands appear first at high latitudes early in each cycle, then migrate toward the equator as the cycle matures, converging near the equator just before minimum. This pattern, traced across decades of observation, is called the butterfly diagram. Its shape is the visual record of flux migration across each cycle. The polar coronal holes track the same underlying rhythm. During the quietest phase of the cycle, a polar coronal hole can cover an enormous fraction of the upper or lower hemisphere. In ultraviolet light, the dark region extends from the pole down to roughly 60 degrees latitude, sometimes further. The boundary is not straight or smooth. It wanders irregularly, with bays and peninsulas of open field intruding into the surrounding closed-loop corona, shifting over weeks and months. Then, as the cycle advances toward maximum, the hole begins to shrink. Opposite polarity flux migrating poleward increases the complexity of the field. Eventually, at solar maximum, the polar coronal hole can be almost entirely absent. Small isolated holes appear at scattered latitudes instead. After the reversal, the holes gradually rebuild with opposite polarity, growing back toward full size as the cycle approaches the next minimum. The size of the polar coronal hole is a real-time indicator of where the sun stands in its cycle. And here is the engine behind the whole machine. The sun does not rotate as a solid body. Its equator rotates in roughly 25 days. Its high latitudes take more than 30 days to complete the same rotation. This is differential rotation, and it is one of the fundamental drivers of everything the cycle produces. Think about what that difference means for the magnetic field threading through the sun. The equator is pulling ahead of the poles, year after year, cycle after cycle. The field lines stretching between those regions cannot follow both simultaneously. They get dragged, stretched, wound increasingly tight around the sun's interior, as the equatorial rotation progressively outpaces the higher latitudes. That winding builds up twisted, complicated magnetic structures. Those structures eventually surface as sunspots and active regions. The energy stored in that winding eventually releases as flares and coronal mass ejections. The winding eventually becomes so complex that the polar fields reverse to relieve it, beginning the cycle again. Below the visible surface, the deep interior also rotates differentially, with patterns that vary by both latitude and depth. These patterns can be probed by listening to the sun's own internal oscillations, a technique called helioseismology. The boundaries between regions of different rotation rates inside the sun are where the strongest magnetic field generation is thought to occur. The poles play their role in that deep interior architecture as well, though the precise mechanisms are still being worked out. The full picture resolves into a long causal chain. Deep interior rotation generates field. Convective layers carry it upward. It surfaces as sunspots and active regions at mid-latitudes. It migrates poleward over years, it accumulates at the poles, it cancels the existing polar field and flips it. And that new polar field becomes the seed for the next cycle. The poles are not the end of the chain. They are the end station and the memory store both at once. What that chain looks like in practice, how it was finally measured from a vantage no mission had ever reached before, was the next question waiting to be answered. That question had been waiting for a long time. The chain leads to the poles. The poles drive the cycle. The cycle shapes everything the sun does across its entire working life. And yet for most of the history of solar science, no instrument had ever looked down at those poles from above. No spacecraft had ever climbed out of the plane to see them at close range. The question of what the polar regions actually look like, measured directly, sampled from a vantage that could resolve their structure, had gone unanswered for decades. 2 missions changed that. Only 2 in the entire history of spaceflight. Both stories are remarkable, both are partial, and the first one started by flying in the wrong direction entirely. The first mission was a joint effort between a North American and a European space agency, years in the planning, launched from low Earth orbit, aboard a winged orbital vehicle. The spacecraft itself was small by the standards of interplanetary probes, a single large dish for communication with Earth, a spinning body to keep its instruments distributed evenly, pointed outward in all directions as it rotated. It carried instruments to measure magnetic fields, solar wind particles, energetic ions, dust, radio waves, and cosmic ray populations at high latitudes. What it did not carry was a camera. No high-resolution telescope. No imaging system for the sun's surface or detailed coronal structure. The mission's purpose was to measure the environment above the plane, not to photograph it. The trajectory was the first reveal. Here is what most people would assume. To reach the sun's polar regions, you fly toward the sun. You climb perpendicular to the planetary plane, gaining altitude above the ecliptic until the poles come into view. That is the obvious path. That is not what happened. The spacecraft launched outward, away from the sun, on a long, curving path toward Jupiter. It flew for more than a year in the direction of the outer solar system, crossing the orbits of the inner planets, crossing the asteroid belt, falling into Jupiter's immense gravitational field from a carefully computed approach angle. And then, Jupiter redirected it. Not to speed it up toward the outer system, not to send it towards Saturn or beyond. It bent the spacecraft's trajectory sharply out of the plane, tilting its orbit by roughly 80 degrees relative to the ecliptic, almost perpendicular to the disk of everything else in the solar system. The reason this maneuver was the only viable option comes back to delta phi. To tilt an orbit by 80 degrees through direct thrust, from low Earth orbit, would have required many tens of kilometers per second of velocity change. No chemical rocket can deliver that. No rocket ever built comes close. The Jupiter detour provided essentially the entire inclination change for free, borrowing it from Jupiter's own orbital motion rather than buying it with fuel. The trajectory took years longer than a direct climb would have, but a direct climb was never actually available. The Jupiter detour was not a shortcut. It was the only path that existed. After the encounter, the spacecraft began looping around the Sun on its tilted orbit, climbing high above the ecliptic at one extreme of each pass and diving deep below it at the other. And it measured. The scientific harvest was substantial. The mission confirmed by direct in situ measurement for the first time that fast solar wind streams predominantly from polar regions and slow solar wind from low latitudes. That origin had been inferred from theory and from ground-based observations for years. Now it was directly verified, sampled from the right vantage, the wind itself measured at high latitudes as it flowed outward. The polar coronal hole was not just a model, it was a working factory. The instruments confirmed it. The mission also confirmed the ballerina skirt geometry of the heliospheric current sheet. As the spacecraft climbed to higher latitudes, it crossed the current sheet less and less frequently, exactly as the equatorial sheet model had predicted. The geometry was real. The spacecraft had mapped it from a vantage that could see how the crossings changed with elevation above the plane. Then there was an unexpected finding. The large-scale structure of the Sun's magnetic field at distance turned out to be surprisingly uniform across latitudes. Near the immediate polar regions, the field was as polar as surface measurements suggested. Open field lines stretching cleanly outward from the coronal holes. But farther out, the radial component of the field became roughly the same in all directions. Smoothed, equalized. The solar wind plasma was carrying the magnetic field outward across the entire heliosphere, blending what had been a strongly structured polar field into something more globally uniform. More local near the surface than expected. More global at distance than expected. The structure shifted character depending on where you measured it. The mission operated for nearly 2 decades before its instruments fell silent. It is still there. The orbit continues. A perpetual high inclination loop around the Sun, the spacecraft carried along inside it, inert now. The dish no longer transmitting. No rescue is planned. No successor is flying the same orbit. The silent spacecraft makes its loops above and below the solar plane, year after year, with nothing left to send home. It is one of the quiet artifacts of human spaceflight. Let that image settle for a moment. But there is one thing the first mission never did, despite everything it accomplished. It never took a picture. The visual landscape of the Sun's polar regions, the actual appearance of the polar surface and corona from above, remained almost entirely unknown when the mission ended. The closest thing to a polar image that existed afterward was a foreshortened view from within the ecliptic. The pole tilted toward the observer at a shallow angle, most detail collapsed into projection and lost. The environment above the plane had been measured. It had not been seen. The second mission came decades later, European-led. A different strategy from the beginning. Instead of one decisive Jupiter encounter to tilt the orbit sharply and permanently, this spacecraft uses repeated flybys of Venus. Each pass adds a small number of degrees of inclination. A few degrees at a time over many years across many flybys, the orbit climbs steadily out of the plane. It is not a single dramatic leap. It is a long, patient accumulation of borrowed geometry, the same principle as the first mission but distributed across time rather than concentrated in one moment. The instruments are a deliberate complement to what the first mission lacked. A high-resolution telescope for visible light imaging of the solar surface. A magnetograph for measuring surface magnetic fields directly, latitude by latitude. Ultraviolet images for capturing the corona and chromosphere. Coronagraphs that block out the Sun's bright disk to reveal the fainter outer corona. In situ instruments measuring the local solar wind and magnetic environment, carrying forward the measurement tradition of the first mission. It is, in effect, a flying solar observatory, built to do what 400 years of equatorial observation could never do. The orbit brings the spacecraft close to the Sun at perihelion, close enough that thermal management is a genuine design challenge. A specialized heat shield protects the instruments from the intensity of sunlight at those close approaches. Small doors in the shield open briefly when the spacecraft is far enough from the Sun for the optics to look out safely. The surface treatment reflects as much light as possible. The thermal problem is significant but solvable, demonstrated to work across multiple close approaches. And then, recently, the spacecraft began reaching the inclinations needed to image the polar regions. The first direct close images of one of the sun's poles were returned, not from within the ecliptic, looking up at a foreshortened rim, from above the plane, looking down, at an angle that allowed real structure to be resolved for the first time. Wait, consider what that means. The sun has existed for 4.5 billion years. Humans have studied it with telescopes for 4 centuries, and the first time we saw a polar region directly at meaningful resolution was recently. There is no archive footage from before this. There simply is none. The first frames of the South Polar region did not look like the equator. The surface texture was finer, more chaotic. The magnetic field was a tangle rather than a pattern, countless small flux concentrations woven together rather than the broad, organized active regions familiar from equatorial images. Polar plumes extended outward from the polar coronal hole as individual rays of plasma, resolved now as distinct structures, leaning gently with the curvature of the rotating magnetic field. Not a simplified version of what we already knew, a genuinely different landscape. Together, the 2 missions form the entire record of human experience, above the plane. The first proved the polar regions behave differently from the equator. Different wind, different field, different particle environment. The second is filling in what the first could not reach: direct imagery, magnetic maps, the visual character of the polar surface itself. Between them, they demonstrated that the out-of-plane vantage is not a luxury. It is a requirement. The sun cannot be understood as a 3-dimensional object from inside the plane any more than the interior of a building can be understood from the street outside. But even combined, neither mission has been able to hover. Both have moved through polar latitudes on their own inclined orbits, sampling briefly, then sweeping back through whatever portion of the disk their trajectories next carried them. The polar regions have been visited. They have not been lived with. Progress compared to no polar observations at all is enormous. The remaining gap compared to what a sustained polar observatory could measure over years of continuous watching is also enormous. Both things are true at once. The sun's poles have been opened as a subject for the first time. What remains to be learned there is still almost everything. Pull back further now, past the polar plumes, past the fast wind streams pouring out from the coronal holes above and below, past the planets, the asteroid belt, the scattered disk of icy bodies beyond Neptune. The sun's reach extends much farther than any of that. The solar wind does not stop at the edge of the planetary system. It keeps going, thinning gradually, slowing, carrying the sun's magnetic field outward across distances vastly greater than anything the planets occupy. And eventually, far out in the darkness, it runs into something it cannot push through. The surrounding galaxy has its own gas, low density, mostly hydrogen, drifting slowly between the stars. The solar wind streams outward, and this interstellar gas pushes inward. At some distance from the sun, the 2 pressures balance. The wind can go no farther. A boundary forms. That boundary is called the heliopause. The great bubble of solar plasma enclosed within it is the heliosphere. Everything we have ever explored, every planet, every moon, every asteroid, every comet we have watched swing past the sun, lives deep inside this bubble. Not near the edge, deep inside. The heliosphere is our local weather system, our magnetic environment, our shield against the harsher conditions of the interstellar medium beyond. Here is what scientists believed for most of the late 20th century. The sun moves through the surrounding interstellar gas at roughly 26 kilometers per second relative to the local medium. That motion, they reasoned, should compress the heliosphere into a rounded nose on the upwind side, where the moving sun pushes into the gas it sweeps through, and stretch it into a long tapering tail on the downwind side. Picture a comet moving through space with a bright, rounded head and a long, flowing tail streaming behind it. The heliosphere, in this picture, had that same basic shape. The comet model fit much of the available data. It made specific predictions about where the upwind boundary should sit, how the magnetic field should behave in the boundary region, and how far the downwind tail should extend. For most of the late 20th century and into the early 21st, it was the working picture. Then the measurements arrived. Two spacecraft, launched generations ago, are still traveling outward today. They are the only human-made objects ever to have crossed the heliopause and entered interstellar space. Their measurements are the closest thing we have to direct observations of the boundary itself, and what they measured was richer and stranger than the comet model had predicted. The field behavior near the boundary was unexpected. The transition itself was more complex. The simple gas dynamic picture did not survive contact with the actual data. Then the data shifted. Both spacecraft crossed the boundary near the upwind nose, roughly within the plane of the planets. That means they could not observe the tail. They could not observe from above or below. They sampled only the small portion of the boundary lying along their own trajectories. We built our entire mental image of the heliosphere's shape from two crossings, both in the same general direction. The comet model was always an inference. It was never a portrait. We had never seen the heliosphere from outside its own plane. A more recent model changes the picture entirely. Astronomers studying how the interstellar magnetic field interacts with the solar wind at the boundary have proposed a very different geometry. In this model, the heliosphere does not have a long tail. It looks more like a deflated croissant, two lobes curving back from the upwind nose with a narrow waist between them, and no extended tail at all. The sun's magnetic field, threaded through the solar wind and strong enough at the boundary to pinch the bubble closed on the downwind side, prevents the long-tail geometry from forming. The bubble is more compact. Its shape is more like a curved shell than a flowing teardrop. And critically, this model predicts that the boundary on the downwind side would sit much closer to the sun than the comet picture implied, perhaps not much farther than the upwind boundary itself. The comet model says the tail stretches far. The cross-on model says there is no tail. Those are not small differences. Those are two fundamentally different shapes for the space we live inside, and the data cannot yet decide between them. The geometry is hard to reconstruct from measurements taken within the plane alone. The truth may lie somewhere between, or in a configuration neither model has imagined. No instrument, no telescope, no spacecraft has ever seen the heliosphere from outside its plane. We have mapped this solar system, planet by planet, across centuries of careful observation. Its outer boundary, the soft edge that separates the sun's reach from the rest of the galaxy, has never been drawn. The workaround being developed does not require a spacecraft to fly to the boundary. Energetic neutral atoms offer a different path. Here is how they form. Charged particles from the solar wind stream outward. Neutral atoms drift inward from the interstellar medium. Where they meet near the boundary, electrons transfer between them. The result is a fast neutral particle, no longer bound by magnetic fields, traveling in a straight line back through the heliosphere toward the inner solar system. These returning neutrals carry information about where the interaction happened, which means they carry information about the structure of the boundary itself. Mapping the directions and energies of particles arriving from across the full sky builds up an image of the boundary without traveling to it. The technique resembles the way a medical imaging machine reconstructs internal structures from particles arriving from many angles. Inference, not direct sight, but inference that works. An earlier mission produced the first all-sky maps of the heliospheric boundary using exactly this technique. Those maps revealed something no one had predicted. A bright ribbon of enhanced neutral atom emission stretching across the sky in a particular geometric pattern. Its origin is still being worked out, but its existence demonstrated that the boundary region has more structure than the simplest models had imagined. A new probe is being prepared to refine those maps significantly. Sharper resolution, better discrimination between competing geometries. It will not fly to the boundary. It will orbit close to Earth and listen to the particles that arrive from every direction. The portrait of our home will be assembled from the inside, particle by particle. The boundary itself is not static. It breathes. During solar maximum, when the wind is more intense, the bubble pushes outward and the heliopause moves farther from the sun. During solar minimum, the wind gentles, the bubble retreats, and the boundary draws inward. The two spacecraft that crossed the heliopause did so at different phases of the solar cycle and measured different distances. Neither crossing was measuring the same boundary. The interstellar medium surrounding the bubble is not uniform either. The Sun is currently passing through a small, relatively low-density region of interstellar gas called the local interstellar cloud. That cloud is itself embedded within a larger, even lower density cavity called the local bubble, thought to have been carved by ancient supernova explosions tens of millions of years ago. Massive stars burned out, exploded, and swept the surrounding gas outward, creating a vast, relatively empty region through which the Sun now drifts. Our heliosphere sits inside a bubble within a bubble. The inner bubble made by the Sun's wind. The outer bubble made by supernovae of stars that died before the solar system existed. When the Sun eventually drifts out of the local interstellar cloud into a different region, conditions at the boundary will change. A denser environment compresses the heliosphere inward. A lower density environment lets it expand. The boundary is not a wall. It is a balance, shifting as the pressures on both sides shift. The heliosphere we know today is not the heliosphere the early solar system had. It is the most recent in a long history of heliospheres, each shaped by the interstellar environment the Sun was passing through at the time. Think about the full picture now. A planet inside a star's gravitational reach. The star inside a bubble of its own wind. The wind bubble inside a low-density interstellar cloud. The cloud inside a larger cavity carved by ancient supernovae. That cavity inside a galactic spiral arm. The spiral arm inside the disk of the Milky Way. The disk inside a small group of galaxies. Each shell nested within the next. Each boundary a balance between the pressure pushing outward and the pressure pushing in. The solar system is not simply a collection of planets orbiting a star. It is a structure within structures, all the way out, each layer marking a different kind of boundary between what the Sun controls and what controls the Sun. We do not fully understand the shape of the second shell from the inside. The heliosphere's geometry remains one of the genuinely open questions of contemporary astronomy. The new probe will help. The two distant spacecraft still transmitting will keep adding data. But the question that would settle it, a spacecraft crossing the heliopause from above the plane, perpendicular to the disk, measuring the boundary in a direction no mission has ever sampled, remains a mission that exists only on paper. The architecture is understood. The vehicle does not exist. And the picture of our own home, the first true portrait of the bubble we live inside, is still waiting to be made. But the question, for tonight's purposes, is not only what is missing. The question is how we would actually get there. How a spacecraft would climb out of the disk that has held every human mission in history. Not by brute force. The brute force answer was settled in an earlier part of this journey, 30 kilometers per second, perpendicular from low Earth orbit. No rocket ever built comes close. But there is another answer, and once you hear it, it carries the quiet inevitability of geometry. To climb out of the plane, you fall in first. Not toward the outer solar system, not away from the Sun, toward it, closer than any of the planets, closer than Mercury, falling inward, accelerating, gathering speed as the Sun's gravity pulls the spacecraft down into the deepest gravitational well in the solar system. And then, at the bottom of that descent, the engine fires. This is the principle sometimes called the deep well burn, or the perihelion maneuver. It is one of the most beautiful ideas in spaceflight. The reason it works comes down to how kinetic energy behaves. Energy gained from a burn does not scale evenly with the fuel spent. It scales with the square of the velocity at the moment of the burn. A kilogram of propellant burned when the spacecraft is already moving at 100 kilometers per second changes the energy budget far more than the same kilogram burned at 10 kilometers per second. Same fuel, same thrust, completely different result. The existing speed amplifies what the fuel accomplishes. The same principle governs every interplanetary mission ever flown. When a spacecraft arrives at a planet and fires its engine to enter orbit, the burn happens at the closest point of approach, because that is where the spacecraft moves fastest and the fuel works hardest. Every interplanetary departure works the same way. The deep well burn is not exotic. It is standard. What changes tonight is the scale. The Sun is the deepest gravitational well in the solar system. A spacecraft falling freely from Earth toward the Sun reaches well over 100 kilometers per second at closest approach. The Sun's own gravity provides that speed at no fuel cost. Geometry does the work. And then, at perihelion, the moment of greatest speed and greatest peril, the engine fires briefly. Not for long. The burn can be short because the geometry is so favorable. After the burn, the spacecraft rises again, but it rises on a completely different orbit. With the right burn direction, that orbit carries it steeply out of the plane. A trajectory that would have cost 30 kilometers per second of brute force perpendicular thrust can be replaced by something in the range of 3 to 4 kilometers per second, applied at precisely the right moment. Not a modest improvement, a factor of 10. The catch is thermal. Near perihelion, the Sun fills the sky in a way it has never filled the sky from anywhere a spacecraft has traveled. The heat load on the sun-facing side rises rapidly. A specialized heat shield is required, the kind that modern solar probes have already demonstrated at closed solar distances. The thermal engineering is serious. It is also solvable. The bottleneck is not physics. The bottleneck is engineering priority and funding. But there is another way. The deep well burn is only one path. There is another path that carries no fuel at all. A solar sail is exactly what the name suggests. A vast surface, thin as a few microns of reflective film, stowed compactly and deployed in space to catch the pressure of sunlight. Each photon that strikes the sail and reflects imparts a tiny push. A single photon push is unimaginably small, but integrated across a sail surface measured in thousands of square meters, integrated across months and years of continuous sunlight, the accumulated momentum becomes real, meaningful. A sailcraft can spiral inward or outward without burning a gram of propellant. By tilting the sail at different angles relative to the Sun, the spacecraft can add energy to its orbit, subtract energy, or rotate the plane of the orbit itself. The same basic principle that a sailing ship uses against the wind. The sail can do work no chemical rocket could afford over the same interval. The technology has been demonstrated on small missions. The film is manufacturable. The deployment mechanisms are understood. What has been missing is the scale, the funding, and the political will to build a sailcraft large enough to perform a serious polar solar mission. Concepts have been studied for decades, some refined in considerable detail. None has been built. The sail's fundamental limitation is time. Thrust is gentle. Trajectories take years longer than a perihelion burn path. The mission shapes itself slowly, but the sail does not run out of propellant. As long as the Sun shines, thrust continues. Mission lifetime is bounded only by sail durability and spacecraft electronics, not by a fixed fuel reserve. The most promising architecture combines both. A sailcraft deploys from Earth and uses sunlight pressure to spiral inward without burning fuel, doing the slow, patient work of getting close to the Sun. Approaching perihelion, the sail furls or is released. A small high-energy stage performs the perihelion burn at closest approach. The sail does the cheap, slow work. The perihelion burn does the brief, decisive work. The resulting trajectory climbs steeply out of the plane into a polar orbit around the Sun. Neither approach alone could achieve this profile in a reasonable mission lifetime at acceptable cost. Together, they become something neither could be alone. Variants of this combined architecture have been studied, refined, modeled, and shelved repeatedly, waiting for the right alignment of scientific priority, funding cycle, and political timing. None has yet been built. Beyond the sail and the perihelion burn, other options exist. Ion engines, which accelerate ionized propellant to very high exhaust speeds using electrical power, deliver small continuous thrust over years, and have already performed maneuvers on interplanetary missions that chemical rockets could not have afforded. Given enough power and time, ion propulsion can accomplish enormous, total velocity changes. Nuclear electric propulsion, a small nuclear source providing electricity for high-efficiency thrusters, would offer even greater capability. More power than solar panels can provide, especially far from the sun. A nuclear electric spacecraft could climb out of the plane, hold a polar vantage for years, maneuver freely, and observe continuously. The technology has been studied in detail. It has not been flown at the required scale. The unifying principle across all of these approaches is the same one that has run through this entire journey. The universe rewards working with the gravitational landscape rather than against it. The deep well is not only the obstacle, it is also the lever. Used at the right moment, in the right direction, with the right preparation, the sun's own gravity can deliver a spacecraft to a vantage no straight ascent could ever afford. The missions are possible. The sun's polar regions are not beyond reach. They are simply beyond the reach of the kinds of missions we have so far chosen to build. Now suppose the choice has been made. Suppose the architecture was selected, the spacecraft assembled, the trajectory flown. Suppose the mission is real. The spacecraft is above the sun's north pole or below its south pole at a comfortable distance, in a slow, patient orbit, allowing continuous observation. Instruments functioning. Communications stable. What would it see? The first change would be the sky itself. From inside the ecliptic, the night sky carries the zodiacal glow, sunlight scattered by the dust disk that the second part of this journey described. Gentle but persistent along the ecliptic, it limits how faint a star or galaxy can appear from any in-plane vantage. From above the plane, that glow lies behind and below the spacecraft. It no longer scatters upward into the field of view. The sky overhead would be cleaner than any view obtainable from anywhere inside the solar system. Distant stars seen against a darker background. Faint galaxies less obscured. The cosmic microwave background, the faint relic radiation from the universe's earliest light, measured with less solar system foreground than any telescope in the disk has ever managed. Temperature variations in that ancient radiation, the tiny imprints of structures from before the first stars, would become more precisely measurable. Nearly every cosmological measurement improves slightly when the foreground is reduced. Telescopes searching for biosignatures in exoplanet atmospheres face competition from zodiacal scattered light at every wavelength relevant to atmospheric chemistry. From a polar vantage, that competition is dramatically reduced. The faintest signals from distant worlds become slightly easier to extract from the background. Even ordinary time domain astronomy gains. Variable stars, pulsar timing, long-duration monitoring of faint transient sources, all improved by a darker, less obscured sky. The local environment would shift as the spacecraft climbed. Close to the equatorial plane, the solar wind is slow, turbulent, variable, threaded with the rippling current sheet. Climbing to higher solar latitudes, that environment transitions into something faster and smoother. The fast wind from the polar coronal hole, more uniform and less variable than the streamer belt wind below. The boundary between the two is not a wall. It is a gradual transition, with mixed regions where fast and slow winds interact. Compression fronts where faster wind overtakes slower wind. The first polar mission mapped these transitions at low resolution and found more structure than the simplest models had anticipated. A sustained mission would map them in a detail that one brief survey pass could never achieve. The spacecraft's instruments would also measure cosmic rays arriving from outside the solar system. Galactic cosmic rays reach the inner solar system at rates that vary with latitude, because the heliospheric magnetic field deflects them as they travel inward, and that deflection depends on field geometry at different latitudes. A sustained polar mission observing across many years would help untangle how the heliosphere modulates the galactic background at high latitudes, in directions that the two missions we described in the 9th section of tonight's journey were never positioned to sample for long. Then turn the instruments downward, toward the plane. The disk of the solar system would appear, for the first time in human history, in plan view. Orbits of the planets visible at a glance, not inferred from in-plane observations accumulated over centuries, but seen directly as a geometric pattern laid out below the spacecraft. The inner system in a single field of view, Earth and Venus and Mars as small bright points threading slowly along their paths. The slight tilts that distinguish one planetary orbit from another visible directly. The asteroid belt as a faint band, its distribution and the resonance gaps carved by Jupiter's gravity resolved across the belt's full width. Trojan asteroids sharing Jupiter's orbit, visible as clusters. Dust contributed by short-period comets and by icy bodies beyond Neptune resolved against a darker background. The various dust sources distinguishable for the first time. That image does not exist. It has never been taken. It cannot be taken from any vantage within the plane because the plane's geometry forbids it. A camera inside a flat disk cannot photograph the disk from above. Only a spacecraft above or below the disk can do it. No spacecraft has ever held that vantage long enough to make the image. The first plan view portrait of the solar system as a single object is one of the great unfinished photographs of astronomy. A mission that climbed far enough outward on its inclined orbit would also finally answer the question that ran through the 10th part of tonight's journey: the comet shape or the deflated croissant. The two models predict different boundary geometries at high latitudes, different distributions of magnetic structure in the regions above and below the disk, different downwind configurations. A polar spacecraft sampling those regions directly would discriminate between them. If the spacecraft eventually crossed the heliospheric boundary from above or below, it would return the first measurements ever taken of the heliopause outside the disk, the equivalent for heliospheric geometry of what the existing boundary crossings near the upwind nose established for the forward direction. Either result would be transformative. Confirming the comet shape would clarify how the sun's magnetic field shapes the downwind structure. Confirming the croissant would rewrite the picture entirely. Either way, the portrait of our home would finally carry a clear outline drawn from direct observation, rather than from inference. Look further outward from the polar vantage and the galactic sky comes into an unfamiliar arrangement. The Milky Way's disk, tilted roughly 60 degrees relative to the ecliptic, as the second section of this journey described, would rise as a great slanted band across the sky in a configuration no human eye has ever seen from anywhere but the ground. The direction below the sun's south pole opens into one of the clearer sightlines through the local bubble carved by ancient supernovae. Foreground gas thinner, obscuring dust less dense. A telescope pointed in that direction would have a particularly clean view out into the wider galaxy. The local bubble's own structure, elongated, with chimneys extending vertically out of the galactic disk, would be visible in directions that in-plane observations cannot resolve clearly. There is no photograph of the solar system from outside its plane. There is no photograph of the sun taken from directly above one of its poles at full resolution in steady conditions for long enough to study its dynamics over time. These images do not exist. They are not impossible. The engineering is real. The principles are old. The trajectories have been calculated. The mission concepts have been worked out. We simply have not flown the mission. Every direction we have ever looked from has been a direction within the disk. Our solar system is a flat thing, and we have been observing it from inside its own flatness for the entire history of astronomy. The poles of the sun, the top and bottom of the heliosphere, the vertical axis of the disk itself, all of it lies in a region visited only briefly by two spacecraft, neither of which could do more than sample what was there. The first comprehensive view from above is still missing from our records. It is one of the few remaining gaps in the local map. It can be filled. It has not been filled. The sun has waited 4.5 billion years for the first sustained look from above. It can wait a little longer. What is missing is not the engineering. What is missing is funding, political will, and patient agreement among the people who plan these things that the vantage is worth the cost. The vantage is worth the cost. The flatness of our solar system has shaped every photograph of the sky we have ever made, every spacecraft trajectory ever flown, the orbital mechanics of every mission, the geometry of every observation, the limits of what every telescope can resolve. The plane is not a mistake. It is the natural outcome of how a solar system formed, holding onto its shape across 4.5 billion years. We have lived inside that shape for the entire history of our species. We will continue to live inside it. The only question, the question that has slowly worked its way through tonight's entire journey, is when we will choose to look at it from somewhere outside. The sun turns slowly, as it has always turned, at the still center of the disk. The planets orbit as they always have. The fast wind streams from the poles as it always has. The current sheet ripples outward as it always has. The heliosphere holds its shape, whatever shape it actually is, against the surrounding interstellar gas. All of this happens, has been happening, will continue to happen, whether or not anyone is watching from the directions that would let the watching be complete. The processes do not need the photograph. The photograph is for us. The missing view is not a loss. It is a promise, waiting patiently for the trajectories we have not yet flown.